Welcome back to the lab. Are you ready for an adventure? Oh, I hope so, because we have a lot to talk about. What a stream! We're so close to nailing this design down. Oh, right. Context. We left things off while fighting with the 12-volt buck converter, but today we're cranking things up a notch. We're going to add the 5 and 15-volt bucks into the fray along with a couple supervisory circuits. Sound good? Great. Personally, I don't care if this video needs to be 30 minutes long. I'm not stopping until we're done. I'm not finished until we've calculated line regulation, load regulation, efficiency, and captured the transient response of these buck converters. Before we dive back into the lab, I want to briefly talk about how a buck switch-mode power supply works. I want to give a little refresher on the theory behind this type of power supply. And what you see now is a diode-rectified PMOS version of a buck converter. Pretty cool stuff. There are 3 critical nodes here: the input voltage, output voltage, and the switch node. Okay? When the switch is on, or the gate voltage is at its lowest voltage, current is building in the inductor L2. When the switch turns off, the inductor attempts to keep current constant, and it does this by pulling current through the diode D1. It can't pull the current through the MOSFET, so it pulls it through the diode instead. This transition isn't perfect because this particular diode turns on pretty slowly, which leads to some time when both the diode and transistor are sharing some current, which is not ideal. In fact, this would actually lead to a relatively low efficiency for the converter, and suggests that perhaps one should not casually grab the first rectifier diode they see in LT-Spice when designing a diode-rectified buck converter. Funny how that works. To summarize what we've seen so far, we're taking pulses of current from the voltage source at Vn, we're building current in the inductor L2, and this current continues to flow through the inductor and diode D1 when the transistor M1 turns off. More importantly, we're turning that transistor on and off with a particular duty cycle that corresponds to a voltage ratio between input and output, and the less time this transistor spends on, the lower that output voltage will become. The lower voltage will be observed at the output of this buck converter. Speaking of outputs, what's happening on the other side of this inductor? Well, the current through the load is approximately constant, and we can see this is true pretty simply by plotting it in LT-Spice. Since the load current is approximately constant, that means there's got to be something interesting going on here. Our inductor current is triangular in shape, centered on that load current, but there's a significant quantity of current both above and below that level, so how is the load current constant? Why isn't the voltage changing? Where's the current going? Well, if current is flowing through the inductor, but not through the load, this must have something to do with that output capacitance. The 22 microfarad capacitor on the output must be temporarily absorbing the extra energy coming through the inductor L2, and then providing that energy back to the load later. In this particular instance, a negative current in that capacitor means that it's supplying current to the load, and a positive current in the capacitor occurs when that cap is absorbing current. Current is sloshing in and out of that output capacitor every switching cycle, and that's establishing an approximately DC output voltage around a particular operating point. It's DC with just a little bit of voltage ripple at our switching frequency. To drive this point home, I want to plot the subtraction of capacitor current from the inductor current. Notice, this combined mathematical current has become exactly the same as the load current. Not approximately the same, exactly the same. They must be. This is Kirchhoff's current law, or KCL, at work. The sum of all currents in and out of a circuit node must be equal to 0. Good stuff. Unfortunately, that's all the time we have for theory today, but we have an old video on buck converters if you want more. As we transition out of theory and into practical applications, I need to give On Semiconductor a massive shout out. Their design tool for this controller, and most simple PWM controllers for that matter, CompCalc, is amazing. This is, in my opinion, the pinnacle of design tools for switch-mode power supplies. This tool sets the gold standard for what all silicon manufacturers should strive for. It allows for accommodating input filters in a control loop, tuning control loops to ensure stability. It's awesome. It saved me a ton of time, and I love it. Allow me to show you around. First of all, welcome to CompCalc. This is a safe place where everyone is welcome to speak their mind. What happens in CompCalc? The first thing that needs to be done after opening this tool is understanding whether feedback is implemented as a transconductance amplifier or a voltage error amplifier. That's for the switch-mode power supply controller that we're designing. Ours is a transconductance amplifier, like most of them, and I know this because our compensation components hang off of the compensation pin and connect to ground. With this done, we need to pull in some critical parameters from the datasheet, specifically the VREF value, propagation delay of the bridge stage, inductance value, series resistance, what type of capacitors are being used, and the switching frequency. Boom, done. By flipping through the tabs in CompCalc, we can quickly see ripple currents, ripple voltage, transient response, gain margin, phase margin, and, well, pretty much everything we'd ever need or want to know about this power supply. After just a few short minutes of our time, we've completed a shockingly complete evaluation of this power supply. That is, assuming the math baked into this tool is accurate. Time will tell, I suppose. Assuming it works. Man, I love this tool, and I hope they have a similar one for boost converters. This tool, put simply, is amazing. It feels like cheating. It feels like I'm able to design a power supply way too quickly and way too well. A very thorough analysis with barely any effort. This feels as faster than using WebBench, but I don't feel like I'm neglecting to do stability analysis. I don't have this general feeling like I'm cutting corners. It feels like I'm doing a good job. So, link down in the description, CompCalc, love it, check it out. I suppose that's a great transition into our lab work. How did all that lab work turn out? Do our supplies have sufficient gain and phase margin like CompCalc suggested they should? Do they appear to be stable and function as intended? Is the transient response decent? Well, there's only one way to find out, right? Let's show off some of that sweet live stream footage to save you a bit of time and see how that went. At first blush, I was very happy. We got everything assembled really quickly, everything came up, no showstoppers. All three supplies came up at their specified voltage, 15, 12, and 5. However, after transitioning into some load testing, things got a little explodey. When dropping a large load step on these converters, the low side FETs we're using in these converters tended to fail short, which hit the gate driver at 24 volts, blowing up the switch mode power supply controller. Yikes. Yeah, that's not great. That's not what you want. I think we've found the most probable cause for this failure, but more on that in a second. Switching gears from the 12-volt rail to the 5, we were able to run our full suite of tests. I'm very happy with what we saw when not busy blowing itself to pieces. This design actually works really well. Line regulation was measured to be an excellent 1.15% in the range of 18 volts and 26 volts at a 3 amp load. Not bad. This means that every volt change on the input, the output will change by 1.15% of that 1 volt, or 11.5 millivolts will change on the output for every volt that changes on the input. That's pretty good. Load regulation was a lot less spectacular, but I am personally laying blame on the series PTC. When I measured load regulation at the point where feedback is established, it looks awesome. Near perfect load regulation. But there is a serious voltage drop across the 5 amp PTC, which leads to the worst performance. Which makes me wonder that maybe it'd be better to maintain a stiff 5 volt rail on the main board, utilizing multiple smaller 1 to 2 amp PTCs at the interfaces to each daughter card. It's a thought. I don't know if I'll really do it, but it's a thought. It could serve to improve efficiency considerably and make 5 volts more like 5 volts. But even with the voltage drop across the PTC in our calculation, it wasn't too bad. Calculated around 3%, which means that the output voltage changes by 150 millivolts for every amp of output current that increases. Not great, and again, a big reason why I'm leaning towards removing that master 5 amp PTC. Output voltage ripple was measured to be 1.4%, and cranking the output current up to 5 amps didn't cause any problems, so that's pretty sweet. The efficiency of this converter through the PTC was measured as 74%. Oh, man, that stinks. That hurts a little. Because I know the switch mode power supply is better than that. I know the power supply is pretty good, and we're just burning watts in that PTC fuse. So that PT fuse is really putting a damper on my day right now. Yeah. Transient response was excellent. Shifting gears a little, we completely recovered from a pretty intense 0 to 3.5 amp load step in less than 10 switching cycles. I can't remember the exact number of microseconds, but it was not many. It was very fast. This loop is snappy and stable, that is for sure. I suppose that means it's time to test the 12 volt supply, since we already blasted the 15 volt one into oblivion, and the 12 volt one died pretty immediately. Okay. This is not a fluke. What's going on? Why do these transistors keep failing short? What do we keep doing to break this thing? Well, I want to share a little story about design margin and conflicting requirements. When I was setting the peak current limit for these regulators, I set the limit such that there was plenty of margin, about 15%, between the peak current limit and the expected peak current required to establish a 5 amp output current. There's only one problem with that approach. We're sensing current using the low side MOSFET, whose resistance can increase by a factor of nearly 2.5 over the full temperature range of this part. Basically, I designed the peak current limit with plenty of margin such that it would never ever trip across the full temperature range of the MOSFET, even when that RDS on was multiplied by 2.5. While that seems good on the surface, I didn't calculate the other extreme. I just assumed we would never violate the safe operating area of the MOSFETs being used, rather than calculating the worst case peak current or power in a cold MOSFET minimum series resistance situation, which, by the way, turns out that peak current would be around 15 amps. Yikes. With an input voltage of around 24 volts, a worst case peak current of around 15 amps, plotting the absolute worst case peak power in the safe operating area curve, yeah. Looks like we're on the wrong side of the blowing transistors up line, so that explains the whole transistors blowing up thing. We have a couple options to fix this. We can dial the peak current limit down to 4 or 5 amps or so, which may put this converter at risk of falling out of regulation at heavy load, but improve reliability considerably. We can select a new MOSFET with better pulse power handling capability as well. Just choose a part more suited for this peak power stress. In fact, I'm preparing to do both of those things, not just one of them. Unfortunately, we blew up too many parts, which means that I'm fresh out of switch mode power supply controllers. Looks like I'm submitting a clutch Mauser order before our next video, but I threw some helpful resistor values in the cart alongside that beefier end MOSFET. So we'll get this collection of parts. We'll get this design trimmed up in a hurry, of course. The new transistor is a little more expensive. To save a couple bucks, I'd prefer to dial in the limit that prevents violating the safe operating area of our original transistors first, then use the more rugged part only where required, but I'm not sure if that'll be possible. Before we wrap this up, I want to make a point to mention that the voltage monitor circuits, they work. Not a whole lot more to say than that. They successfully indicate when DC input 1, 2, or both are present, and this information will eventually feed into the mainboard microcontroller. The status changes at an input voltage of 21 volts, which is the level that we're defining as power failure for the 24 volt inputs. We were able to assemble and test the 5 volt buck converter without incident, and we're hot on the trail of a new peak current limit to improve the reliability of this design overall. I think our prototype is really coming together, and I'm so thankful to be debugging these power supplies on a prototype board instead of buried in the bottom of a main board of a UPS under 3 daughter cards. The best part is, many of the circuits to come in this prototype rely on 1, 2, or even all 3 of these voltages being present and functioning, so it was important to build up the core functionality first. If you like what you saw today and can't wait for more, consider subscribing to be notified of our future videos. We're going to be talking about the physics behind Ferrite beads and bringing up the 5 kilovolt isolated dual output Flyback converter. It's going to be awesome. If you want to support the channel, consider checking out the products that we featured today through our Amazon affiliate links in the description. It really helps us out a lot. There's also a link to our sticker giveaway in the description if you're into that sort of thing. So I'm really excited for next Saturday. I'm really excited for where we'll be streaming the next part of this saga. If you think this UPS project is cool, let me know by hitting the like button on this video or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for everyone. Thank you for staying till the end. Bye!